All right, thanks, Mike. So just a little bit about myself. I'm a process controls engineer and automation contractor based in St. Pete, Florida, and my company is JLB Controls. I've done industrial control research and applications for about 11 years now, and I'm really happy to share some of that today. So let's get right into it. All right, model-based PID tuning is the topic of today's webinar. And what makes model-based PID tuning different from other methods is that it focuses on understanding the process that's being controlled. So we're not just going to throw tuning values at a controller to see what works. We're actually going to use real plant data to create a process model. And that model is going to describe how the system reacts to a control signal input. It sounds pretty complex, but actually it's really simple and really effective, especially in process industries, and we'll talk more later about why that's the case. But once we have a process model, it becomes very simple to tune the PID controller. Okay, so I've already hinted at what model-based PID tuning is all about. Next, we'll take a step back and just review PID control and the terminology we'll be using today. Then we'll talk about two generic process model types that are really useful for PID tuning, and bump testing, which is how we generate plant data that we can use to fit a process model, and tuning correlations, which use that model to help select good PID tuning values. Then we'll put everything together with a live example and tune a PID loop. At the end, if we still have time, I'd like to talk about the pitfalls of using PID Autotune, which is generally a very unsuccessful strategy, but it does have a few things in common with model-based tuning, so it's worth talking about to help us avoid similar problems. Okay, let's review some terminology by walking through a PID control example. Here's a PID loop that's controlling water level in a tank. We have a pump, P1, pumping water into tank 1, and level is being controlled by PID controller LC1. So looking at the controller, there's 3 variables here, and these are fundamental PID control variables. But some controller brands do name them differently, so they might not look familiar to everyone. We have PV, which stands for process variable, and that is the measured value that we'd like to control. In this case, it's the tank level measurement. SP stands for set point, which is the target value that we'd like to maintain. In this case, we'd like to maintain 6 feet of water in the tank. And the entire purpose of PID control is to try to maintain that process variable at the set point. And it does that by generating a CV signal, or a control variable signal, which can influence the PV in some fairly predictable way. In this case, the CV signal is used to adjust pump speed, which of course impacts tank level. So I said that CV influences PV in some fairly predictable way, and that detail is what makes PID control possible. The controller needs to have some built-in understanding of the process so it can make appropriate adjustments when PV is not at set point. And the best action to take completely depends on the nature of the process. More specifically, it depends on the dynamic relationship between CV and PV. And that is the relationship that we'll be modeling today. So PID tuning is the way we tailor the controller's behavior to the process that it's controlling. Okay, so we actually covered a lot on that first slide. Let's quickly summarize. We've defined our PID variables. We have set point, process variable, and control variable. And the objective of PID control is to reduce error between set point and process variable. And PID tuning depends on the relationship between CV and PV. And that's the relationship that we'll be modeling. Okay, so here's a more generic view of a PID loop where the process could be anything, not just tank level control. And over here we have the inner workings of a PID controller, including the three tuning values, KP, KI, and KD. So it's helpful to have a working knowledge of the PID calculations here, but a deep understanding actually isn't critical for model-based tuning. We're going to be able to calculate good tuning values and even simulate the effects of tuning changes offline. So you don't need to study that part too hard, but I will quickly go over it now. Just like in our tank level loop, we have a set point and a process variable. And the difference between those is the error. Error is fed into the PID algorithm and used to calculate a control variable with the aim of reducing that error. And the control variable is the sum of three components. The simplest part is just proportional to the current error. That's this one here. The second component is proportional to the integral of error over time. So it considers the history of the error and acts to correct persistent errors. And the last component is proportional to the derivative of error. So if PV is changing really fast, derivative will act against that change, and it can have a stabilizing effect on the loop. This style here is known as the independent PID format. Each component has its own independent scaling factor, which are the PID tuning values. But some controller brands use a different style called the dependent format, which uses a controller gain, KC, which is applied to all three terms, plus an integral time and a derivative time. For now, just be aware that different formats do exist and you can convert between them if you need to. For industrial controls like a PLC or DCS, all of this stuff here is usually handled in a standard software block. So I'm just going to simplify our diagram a little bit. Okay, this looks a little bit more familiar. We have a software function block where all the PID calculations and tuning values live, and the CV output goes to a process, which could be anything. It might have pumps or valves or major equipment like tanks or heat exchangers or a turbine, and it includes measuring devices like the tank level sensor or any electrical signals or software outside the PID. So our definition of the process includes everything that relates CV to the PV signal that goes back to the PID controller. But we're still missing something. In the real world, any number of variables can impact this PV, not just CV. So we're going to call all those other variables disturbances. So here are the disturbances coming in and impacting PV. So the process defines how PV responds to CV, and disturbances include everything else that impacts PV, everything not driven by this CV. So let's take a look at a disturbance example, and then we'll move on to process modeling. Okay, back to our tank level control example. We have our level control loop here, and on the right, I've added a disturbance. Now some of the water can be diverted through this valve. So the valve definitely has an impact on tank level, but it isn't adjusted by our PID controller. It's not driven by CV. So the valve is a disturbance. And that can be a bit confusing. So here's a hypothetical example. Let's say all the water flows through this valve when it's open. Maybe it's a big drain pipe and completely starves tank 1 of any water supply when this valve is open. So that would completely change the process. Tank level would be totally unresponsive to pump speed at that point. So how can we possibly model a process separate from disturbances when they're so interdependent? And the answer is we can consider some baseline constant valve position to be a fundamental part of this process, and only changes in the valve position are disturbances. So we're going to call those baseline conditions our normal operating conditions. So when we start process modeling, keep in mind that model accuracy can depend on operating conditions, and in some cases you might even want to use multiple models for different conditions. In that situation, you'd end up with multiple sets of tuning values. That's a more advanced strategy called adaptive tuning, but it's not usually needed. For now, just be aware that it's best to model the process during normal operating conditions. So when we're modeling the pump speed to tank level process and our disturbance, this valve usually operates around 30%. We're just going to hold it at a constant 30% when we're modeling. Okay, I've added a couple more bullets to our recap. We've divided the system into two parts. The process, which defines how PV responds to CV, which we know is really important for PID tuning, and disturbances, which are all other variable changes that impact PV. And we also know it's best to model the process at normal operating conditions. So we have our definitions now, we've laid our groundwork, and we can move on to process modeling. So at the beginning, I mentioned that model-based tuning was especially practical in process industries, and here's why. For PID tuning purposes, the majority of continuous industrial processes can be adequately described by one of two simple models. And those are the first order plus dead time model, abbreviated as FOPDT, and the integrating plus dead time model, or IPDT model. So does that mean that these magical models will perfectly match any process that we have? No, it doesn't. Actually, they'll never be perfect, but they do a great job for PID tuning. Okay, here we have a trend of CV and PV for first order plus dead time process. Down here, the model parameters, and there's only three model parameters to describe an FOPDT process. It's gain, dead time, and time constant. So it's a very simple model. The chart shows the PV response to a step change in CV. And we can find the FOPDT values just by looking at this type of chart. Gain tells us how much PV will eventually change per unit change in CV. In this case, delta PV is 10 and delta CV is 1, so gain is 10. Dead time is the delay between a CV change and when PV starts to respond. So it's the delayed reaction. And here it looks like it's about 4 seconds. And time constant is a measurement of how long it takes for PV to respond. So it's defined as the time for PV to make about 63% of its full change. And that looks like about 8 seconds. So that's it. That's all it takes to model an FOPDT process. And here is the integrating plus dead time model, which is even simpler. There's only two parameters here. And again, we have our PV response to a change in CV. So the integrating gain is how much the PV slope changes per unit change in CV. And dead time, again, is a measurement of the reaction delay, the time between the CV change and when PV slope changes.
Hey, Joe.
Yeah.
Do you have any examples of fast or slow loops that you could explain?
Some examples of fast or slow loops?
Yeah.
Yeah, so, again, they could be anything. So one of the slower loops I've dealt with recently is a big industrial dryer temperature control loop. And, that took about 10 minutes for the loop to fully respond, for that product temperature to fully respond to a change in CV. A very fast loop is something like a flow control loop. You change your valve position, and almost instantly, within a second or two, you're going to see the response in flow rate.
So how would that how would that affect the constants in the PID?
So we haven't gotten to the PID tuning yet, but I can tell you it would affect our process model, which is how we're going to derive PID tuning values. So in that case, the time constant for the flow control valve is going to be really short, and we'll see how these model parameters get used to calculate the PID tuning values.
Okay, thanks.
Sure. Okay, so unfortunately, we don't have much time to talk about when to apply each model type, but for the process industry, here's the basic rule of thumb. FOPDT is going to be our go-to choice for naturally stable processes, and we're pretty much going to use IPDT for most other systems. The system on the left, the gravity drain tank, is a naturally stable system. When I increase pump speed, level starts to rise, but as level rises, so does pressure down here. So outflow starts to increase, and eventually PV steadies out at a new higher level. So it's naturally stable. System on the right with pumped outflow is not naturally stable. When I increase pump speed, level starts to fall, and it'll keep falling until the tank is empty. Tank level might impact outflow a little bit, but the effect is really negligible compared to pump speed. So level will continue trending down at a steady pace. It'll never reach a new steady state, so it's not naturally stable. I'd like to point out some nuance here. I purposely wrote not naturally stable instead of unstable. Integrating processes are said to be at their limit of stability, so it's not going to reach a new steady state like the stable process, but it's also not going to start accelerating like an inverted pendulum or a nuclear reactor might. It's going to keep trending down at a steady pace. But thankfully, unstable systems aren't very common in process industries, so IPDT does cover most processes that are not naturally stable. Okay, so let's talk about how we generate that data that we can use to fit a model. And a bump test is a simple way to do that. So here's the procedure we're going to use. We're going to calm our disturbances, and you can just put them in manual near their normal operating level. In our tank example, we put the valve in manual at 30% open. Next, we're going to hold CV constant for PV to settle. So we're going to hold pump speed constant and let our tank level steady out to that new level. And once it's steady, we're going to bump the CV, which just means change it sharply so you can see a real clear response in PV. But remember that we need to model just the relationship between CV and PV. So you want to make sure the bump dominates any other factors beyond any noise or disturbances. And that'll produce really clean data that you can use to fit a process model. Just to clarify, step 2 is a little different for integrating processes, and I'll go back. It's not going to reach a steady state here, so just make sure the slope is steady before you bump for step 2 there. Okay, so now we know what those 2 very useful process models are. We know how to perform a bump test to generate good, clean process data, and we know how to calculate process model parameters using that data. So we know how to get a measurement of process dynamics from a real operating plant. That's the toughest part of model-based tuning. The rest is really straightforward. So let's see how we can use that information for PID tuning.
Hey, Joe, I got another question in here for you.
Yeah, go ahead.
All right, I saw that on the PID objective line, the error will be reduced by the PID function block. Is this adjustable, like a very quick output to correct error, or adjustable, more slower response to error? When
yeah, absolutely.
Especially if it's concerned about overshoot.
Yeah, for sure. That is so that is what PID tuning is going to do for us. It's going to help us shape that response, make it faster or slower, and that will determine whether or not there's some overshoot there as well.
Thank you.
Sure. Okay, so one method to find tuning values now that we have a process model is to use tuning correlations. And these particular correlations are called the Skagestad correlations, which are some of my favorites, but there's plenty to choose from. They're only suggesting proportional and integral tuning terms here, no derivative action, which is actually pretty common. But I'm not showing you these equations so you can memorize them. The takeaway is once you have your process model, you can calculate PID tuning values. Everything on the table is known from our process model. Everything except this blue parameter here, which lets us adjust how fast we want our loop to respond. And so these correlations are a simple way to find tuning values that are a good trade-off between performance, which is how well set point is maintained, and robustness, which is basically a tolerance to modeling errors or changes in your physical process while still maintaining stability. So you can easily look these up whenever you need them. The key point here is once you have your process model, you can calculate some great tuning values. Okay, so let's put everything together with an example and tune a PID controller. We're going to use software to make things easier, but the steps are exactly the same, and you could certainly do it by hand if you wanted to. First, we're going to bump the process using our bump test procedure. Then we're going to fit a process model and select tuning values based on that model. Okay, so we're back with our gravity drain tank. And the first step of the bump test is to put disturbances in manual. So I'll go ahead and do that now. I'll put this valve in manual, and it's around 30%. So I'm going to set that to 30%. Then I'll put the PID controller in manual. Okay, PID controller is in manual. And we're going to allow the PV to reach a steady state. So level needs to steady out at some value. And then I will bump the CV. So we have our pump speed CV around 32 Hertz. I'm just going to bump that up to 45 hertz. Okay, so as our tank level is responding here, Mike, do you have any more questions while we wait?
Yes. Do you advise against using deadband?
Generally, yes. It makes the PID controller non-linear, so it's going to hurt performance to some extent. There are cases where it's going to be useful, but if you can avoid it, just avoid it. I don't have an example where it would be useful off the top of my head right now, but yes, the answer is avoid it if you can.
Oh, and also, how do you know how much to bump it?
Okay, so you want to make sure that you bump the process beyond any disturbances or any noise in the data. In this case, our signal is actually not very noisy, so I could have gotten away with a much smaller bump here. So the rule of thumb is going to be try to make your PV response at least 4 times greater than any noise or disturbances. And if you can, if the process permits, just go ahead and bump it pretty hard.
Okay, and I wanted to get back. I have another question on deadband.
Sure.
The question is, isn't deadband bad as reflected in the formulas?
So that is dead time, which is a little bit different. That's how much reaction delay there is in your process to a change in CV. So one classic example of that is like a transport delay. If you say I started heating, say we're controlling a temperature loop, and I started heating way back here in the pipe. Well, that's really not going to be reflected downstream for a while. So so transport delay is kind of a classic example of a dead time in your process, whereas a dead band is usually sometimes, around a 0 crossing in your PID controller. Maybe you don't want a particular actuator to do anything when you're around a certain PV. So just hold it still and don't upset the process if you're at a certain, around a certain point. So there are definitely some differences there. That answer the question?
I think so, yeah. And also have a question along those lines is, we have someone who has an application where the feedback from the system is delayed by about 10 seconds, chemical dosing point far away from the control point. Can they still use the PID control, or should they use an alternate type of control? I think that's further down the line than before.
Yeah, so yep, it's definitely still a dead time. It's a little bit different in that it's in your measurement, but it's still part of the process here as we've defined it. So the answer is yes, you can absolutely use a PID controller. Its performance is going to be significantly worse than if you had a sensor that gave you live information. But there are some more advanced techniques you can use to kind of help with PID control. So I'd recommend looking up what a Smith predictor does in that scenario to help you kind of net out the effects of that dead time. And who's ever asking the question is certainly welcome to get in contact with me after the presentation. We can talk about that more.
Okay.
All right, so we have our bump, we have our nice response here. I'm going to go ahead and put the controller back in auto so we don't disrupt the process anymore, and put our set point back to 6 feet, and put our disturbance back in auto. So now we have all the data we need. We can let the process do its thing. And I'm going to open up some modeling software that we're going to use for the process modeling and tuning. Okay, so let's find our bump test, which is right over here. Zoom in on that a little better. Okay, here's our bump test here. And let me just pull up my slides. All right, so here's our CV step and our PV response plot. It's a naturally stable process, so I'm going to use the FOPDT process model. And I'll go ahead and fit a model. All right, and sometimes it's good to do that a couple times. But so now we fit the model. We have the gain, the dead time, and the time constant. These are the same calculations we did by hand earlier. I'm just using software to do it for us. So now that we have our model, we can go ahead and tune our PID controller. And we can actually simulate how the loop is going to behave with different tuning values. So down here we have a simulated set point step response, and we can see that PV comes up to meet our new set point. Maybe we want it to be even faster as long as it doesn't overshoot. So we can go ahead and play with our tuning values and try to find a spot where it comes right up and doesn't overshoot. So this slider I'm using here, this is just applying one of those tuning correlations we talked about earlier to find some good tuning values from a process model, and we're just seeing what that simulated response would look like. Okay, but what if the model isn't accurate? Or what if the process changes? Well, we can simulate that too. Say the model was really bad and our process gain was actually twice as much as we thought it was. So we can see, it overshoots quite a bit more, but it is still stable. And we can play with the dead time and time constant as well, just to see what would happen if the process was a little different. So we can simulate a bunch of different scenarios to see how robust our controller is. For our tank level PID, we're actually not trying to track changes in a level set point like in the simulation. We're trying to counteract a disturbance. So let's simulate a disturbance instead. We don't have a model for that disturbance, that valve, but this gives us a quick picture of a generic disturbance that's equivalent to 1 Hertz change in our pump speed.
Yeah, Joe, I've got another question for you, a quick one.
Yep.
Is the PID bot manager a software to use in the field for tuning values or just for this demonstration?
Yeah, it's actually it's meant for the field. It's meant to be used next to a SCADA. It can connect with the same OPC servers that you're using for your SCADA system. So it's meant for the field and for demonstrations as well.
Thank you.
Yep. Okay, so so we're simulating our disturbance here, and we can see that our PID tuning values are holding process the tank level pretty close to that set point, less than or about a 20th of a foot, and we have the response coming down smoothly without overshoot. But before we apply the new values, we probably want to check how they perform compared to our current tuning values. So I'm just going to simulate our current values on top of there as well. And we see that our new values are significantly better. So I'll go ahead and apply these new tuning values. I can add a note in here as well. Reduce disturbance so that we know what we were doing. If back to this. Okay, so the new tuning values are applied and we can see how they're performing. Okay, on the bottom here again is the CV, that pump speed signal, and on the top is the process variable signal. So right about here is when we applied our new PID tuning values, and we're just going to check to make sure that we're performing better, it's doing what we wanted it to do. And before, it looks like we were controlling between 4.5, 5 feet and 7.5 feet. And now with the new tuning values, it looks like it's controlling between 5.5, 6.5 feet. So significantly better control. It responds to that disturbance much better. And we also note that our control effort, the pump speed, is much less. We're swinging around that pump speed much less. So that's always a positive for maintenance as well. Okay, so that's it for the example, unless there was any questions on that. All right, we'll go back to our slides.
I've got a question for you there, Joe. What are the pros and cons of open loop versus closed loop?
Well, feedback control, closed loop control is a pretty magical thing. It really makes everything a lot easier, and that's kind of why PID control is so ubiquitous. Open loop depends on your plant basically being the same over time, no changes. And if you had a perfect model of your plant and you knew it wasn't ever going to change, then open loop control would be just fine. If you always knew what pump speed to be at, you always knew where your disturbance would be, and you always knew what your pressures were going to be. But in reality, that's never the case. You want to use feedback control to correct any problems, or not any problems, but just any changes, any changing situation in your plant. And so that's why it's so commonly used.
Okay, I also have another one on when using electric actuated final control devices. Is there a duty rating entry available to maximize motor life, I guess, on that software, a way that it doesn't work so hard?
So that's going to, of course, depend on the final control element that you're using. So that's not built into the software, and that's going to be a judgment call for the user who's tuning, whether they can tolerate higher, pump speed or not.
Thank you.
Yep. Okay, so if you're anything like me, you're thinking, if model-based tuning works so well and it's just a bunch of calculations, why hasn't someone automated the whole process? Well, they've tried. It's called Autotune, and unfortunately, Autotune usually doesn't work out well. And the reason comes down to this. Most Autotune programs aren't smart enough to handle problems automatically. It really needs to be partnered with someone who can make changes to the plant and who understands the context of all the bump tests and everything else going on, like how much can your final control element tolerate in terms of swings, in so many other factors. And so the problem ends up coming down to Autotune usually hides the modeling steps in the name of being automatic. So they're too opaque for a skilled user to be troubleshooting, and you end up in my somewhat sarcastic Autotune flowchart over here where control is never good and you have no idea what's going on. But most Autotune failures are due to modeling problems. And since that's such an important part of model-based tuning, it's worth going over some of those pitfalls. And I'm going to quickly touch on 5 of them now. Okay, so the first pitfall is disturbances. There's a bump test going on in this plot, and right about here, a disturbance kicks in and contaminates the data. So the model's completely ruined. But that's something you can easily catch. So make sure to look at your data to make sure it makes sense. And more importantly, make sure your disturbances are calm when you're modeling. Second pitfall is equipment problems, and this could take any number of shapes. There's no telling what equipment problems you're going to have, but I'm just using a sticky valve in this example. Here's another bump test with a sticky valve. It appears the valve position gets bumped 10%, but in reality, it's bumped much less. It starts here and only gets bumped up to here. So that ruins the model. The bottom line is you need to know your equipment and make sure the bump test seems reasonable. Number 3 is excessive rate limiting. Rate limiting is used on things like VFDs so you don't accelerate too fast. So it's definitely useful, but if your control signal is heavily rate limited, performance is going to suffer. It also makes modeling tougher because it makes the system non-linear. So if you need a rate limit in your system, when you're modeling, try to use a smaller bump. The smaller bump is going to be less affected by this rate limit. But if you're using modeling software to fit your model, just ramp the CV slower than the rate limit so it's not impacted by that rate limit. Okay, the fourth is noise or a weak bump test. So we can't model the relationship between CV and PV if the PV response is dominated by noise. So again, look at your data and make sure the PV response is clear. Good rule of thumb is that your response should be at least 4 times greater than any noise or disturbances. So in this case, we would probably want to make this bump at least 3 times as hard. And the last one is modeling during abnormal conditions. And this shows 2 bump tests. First bump shows a very small gain. And for the same change in CV, we have a very large gain. So this is a type of nonlinear process, and it shows us why it's important to model during normal operating conditions. If I usually operate my process up here, this is where I need to model the system. I shouldn't be modeling down here. So those are just 5 of some really common ones. But as you get used to process modeling, you'll start to understand what some pitfalls are and what you need to do to generate a good process model. Okay, so let's review some benefits here of model-based tuning to close our presentation. The first 4 bullets are pretty straightforward. We can quickly find tuning values that perform very well, and we can do it with minimal disruption to the process because we do most of that work offline. And it follows a clear procedure, so it's teachable. doesn't rely on years of experience. And this last point is sometimes overlooked, but I think it's really one of the most valuable points for model-based tuning, and that's it helps you understand your process. When you model a process, you're building your understanding of the system and operating conditions. And that helps you reframe your control problems. Instead of talking about bad tuning or wondering when or why tuning was changed, if problems were caused by tuning versus mechanical problems versus material problems, we just completely remove tuning values from that troubleshooting equation. We focus on how the process itself behaves, when and why that behavior is changing. So it separates process behavior from tuning, which is incredibly valuable when you're searching for the root cause of control problems. Okay, so that wraps up the main part of the presentation. So I'll hand it back to Mike to close, and we can get into any remaining Q&A. Thank you.
Thank you, Joe. So like the questions earlier, we are going to upload this to the website, so it will be available recording if you weren't able to catch the start of this. And joining the ISA has a lot of benefits besides the networking events and the breweries. There's also books and virtual events and training and the Intech libraries and all. So reach out to Ed or Russ. Their numbers are there for membership, and we'd look forward to getting together with you on another event. Thank you. Any questions and comments, we can put them in the meeting chat or reach out for the hands up, your call.
Mike, this is Ernie James.
Hey, Ernie.
One of my experiences, when you bump the output, depending on the loop gain, but when you bump the output, you really got to bump it 5%. 1 or 2% often just doesn't give you any feedback due to hysteresis in the valve. And then you compound the problem with the owner doesn't really want you bumping his process 5 or 6%. So one of the tricks I've used is you bump it up 1%, you wait, you bump it down 2, you wait, you bump it up 3, and then you yo-yo it so that when you're bumping it up 5 to get your real data, you're really only bumping it up 2.5 effectively, if you follow that.
Yeah, Joe, you want to weigh in on that?
Yeah, that's a great point, Ernie, and yeah, that's a good rule of thumb. So make sure you're bumping beyond any hysteresis that might be in your valve, and obviously you need to be cognizant of the plant and how they need to operate during your bump test. I will say the bump test is somewhat disruptive, but at least you're not sitting there playing with your tuning values all day, trying to find some good control. So it's usually you rip off the Band-Aid with the bump, and then you can put them right back in auto. Does that wrap it up for the questions, Mike?
Yeah, I don't have any more written, so I'd like to thank everybody for coming.
Joe, hey, Mike, there was a question from Cody up there. It says, when loops cascade, do you tune them separately?
Oh, thank you.
Yeah, that's an awesome question, and I almost actually put that in the presentation today. But the answer is, with model-based tuning, what you're going to do is tune that inner loop first. Take it out of cascade, tune the inner loop first, and then you're going to put that inner loop in auto, and then you're just going to pretend like that inner loop is part of the process. So you do the exact same thing, the exact same procedure for your outer loop. So there's really no change, and that's also another nice thing about this tuning procedure is when things get more complicated, the procedure still remains the same. Anything else, Mike, or from anyone else in the audience?
Yeah, it's looking like we're running low on questions, but maybe Ed, you want to mention anything about the education opportunities?
Yeah, this is Ed Holden. I'm a Tampa Education Chair. So if anybody's on now that would either like to present, or we're always looking for places to host our monthly meetings over at a job site somewhere. I'm down in the southwest corner, down by Fort Myers. So we've got representation over in Deerfield Beach, over that area. Essentially the southeast corner, and we've got board members in the Orlando Space Coast. So if anybody's on this call and wants to generate some activity in any one of those other three areas, give me a call. My phone number, if you want to back up a slide, leave that one up. Give me a call, or we'll figure something else out too. So we're looking forward to getting statewide involvement. That's it. Thanks, Mike.
Thank you, Ed. That's Ed Holden, and it's 303-956-7555.
All right, thanks everyone, and please feel free to reach out to me as well with any questions about the presentation or PID tuning or anything else in general. Really appreciate everyone's time today.